Hello everybody, welcome back to one of our ROMER Talk series presentation seminar. We have today another exciting presentation from Özge Orhan. Özge is our graduate from Mechanical Engineering Department in 2017. Then he continued his studies in Sabancı University in mechatronics, and later Sorry, did I say he? She, it's my bad. She did her PhD in EPFL Lausanne on human-robot interaction and exoskeleton control systems, with a special interest in the partial assistance, balance support, and personalized locomotion strategies. And I think she will present us her PhD work and then what's going on in that area, and inform us about the developments in these exoskeleton research. Stage is yours. Thank you for.
Thanks a lot, Efe. So thanks a lot for the nice introduction and also for your kind invitation. So as you said, I'm going to talk about what I have done through my PhD, and I will talk about different aspects of partial assistance with lower limb exoskeletons to enhance gait and the balance in daily living activities. And as we all know, lower limb exoskeletons can help to many individuals with walking problems, and those people could have those problems because of many reasons. There are many reasons of the mobility problems, and usually neurological disorders are the main causes of the walking disorders, and spinal cord injury and stroke are the two main aspects of the walking disorders. However, there are also other people who can benefit from the lower limb exoskeletons, such as people with neuromuscular disorders and multiple sclerosis. Those people have different needs than the people with spinal cord injury and stroke. Up to date, many of the exoskeletons that exist in the literature and the market, more than 85%, have been all the efforts in research to target those two populations. However, we are not putting that much effort for the people with the neuromuscular disorders and the multiple sclerosis. And this group, we are seeing a patient with neuromuscular disease on the left side and multiple sclerosis on the right side. As we can see, they can also benefit from and help from exoskeleton. And many of those people have conditions that it is going worse and worse because there is no cure for most of the neurological disorders, and there are tons of different variety of the gait disorders that we are having with those people. And also, unfortunately, usually we cannot treat them properly, which is causing them to loss of mobility, which means that after a certain point they cannot walk by themselves and they are prone to fall. And for this reason, we have developed autonomio exoskeleton. As I said, many of the exoskeletons available in the literature are designed for people with spinal cord injury or stroke. And most of those exoskeletons are providing full mobilization, which means that if you cannot walk by yourself, the exoskeleton will gonna enable you to walk again. However, the need of the people with neuromuscular disorders and multiple sclerosis is a bit different. You need partial assistance, and overall, the exoskeleton should be working cooperatively with the user, so we shouldn't be overriding what human needs to do or what human wants to do. And autonomio exoskeleton has 3 active degrees of freedom as hip flexion extension, which is this movement, this one, okay, let me see, okay, this one, and knee flexion extension, this one, and most importantly, hip abduction, that it is allowing us to take the side steps. This is such a crucial degree of freedom, which I didn't know before I start my PhD. Basically, without having this degree of freedom, we cannot keep ourselves balanced when we are walking. And unfortunately, not many of the exoskeletons has this degree of freedom. Therefore, when you are wearing an exoskeleton, you usually need to use crutches to be able to keep your balance. And thanks to the hip abduction, we could actually able to keep our balance. Apart from the degrees of freedom, apart from the active degrees of freedom, we have 3 passive degrees of freedom at the ankle joint, which is also helping us to keep our balance. There are different types of balance strategies, such as ankle strategy, hip strategy, combined strategy, and stepping strategy. Here with this exoskeleton, since we have the passive degrees of freedom at the ankle joint, we cannot provide additional assistance. We are thinking that, or our hypothesis is that the people who are wearing this exoskeleton could able to use their ankle joint by themselves. But what we can help, thanks to hip abduction, adduction, which is the side movements, we can take steps to different directions, and we can change the step positions and the timing depending on the control strategy that it is available. So today I will talk about 3 main topics that I have worked throughout my PhD. First of all, I am going to present how we can provide partial assistance during standing under perturbations. When we push people, what can we do with the exoskeleton, how we can help. And this is not actually just a push, but you can imagine yourself in a bus, and when the bus is suddenly stopping, you still need to take the step. And this is the first part. And later on, I will focus on how we can provide different assistance for different daily living activities, such as walking over ground and stair ascending and descending. And finally, since here we are developing control strategies for overground walking and stair ascending, descending, we also need to be able to understand the transition moments between them so that we can actually provide assistance. So, first of all, what we are doing during standing. So I believe almost everyone here hopefully is healthy and keep their balance, but this is not always the case for people with neuromuscular disorders. And balance loss is a crucial problem, especially with the exoskeletons. As I said, not many of the exoskeletons has hip abduction, adduction, and you have to use crutches. And if you already have the weak upper limb muscles, then you cannot actually use the crutches either. And you actually need to be compatible with what the user wants to do. Therefore, you shouldn't be overriding user movements, and you should be able to take steps to different directions. When you have the perturbations, you can imagine that you are in the bus, you got the sudden stop, you're gonna take the step, and this is what exoskeleton should be able to do. And to be able to do this, we are using divergent component of motion, which is called as DCM. DCM is the known name in robotics, which is also known as capture point. That is also in robotics, but the biomechanics people call this one as extrapolated center of mass, which is exactly the same, which means that how much your center of mass of your body is moving away from a stable position, as here, this is the center of mass position, center of mass velocity, and natural frequency. And this is one of the stability metrics that has been used in the biped robotics overall. And we are getting this idea of DCM, and we are trying to understand if the balance is lost based on DCM, and we are modeling the exoskeleton with the human as a linear inverted pendulum. And we are using the sway area of how much you have under your body as a projection to the ground to be able to decide if you are going unstable or stable. If we decide that your stability is lost, we are running an online optimization problem that is optimizing the step timing. So how long your steps should be taking and what should be the next step position and how much the DCM offset, basically the stability metric, should be. This quadratic programming is run online, and in the end, what we have obtained is that I am here, I get the push or I lost the balance, and this is the next step. And here, now I know this should be my next step, and the exoskeleton should help me to do this movement. And to do so, we are fitting a spline based on human-inspired trajectory. And then we are running this, we are implementing this via an impedance controller so that user has space to be able to make some mistakes. And in the end, we did experiments to understand if this strategy would be working. So, as any experiments, it works up to some point. It doesn't work up to a certain point. And here, how it goes. We have the human here. We are pushing them to different directions. So this is for the first time we could actually able to take different steps with exoskeleton to be able to keep our balance again. And human is standing, we get the push, and then we get the step to here. So the part that it is partially working and partially not working is that this is the point that we are computing, that it is the optimal point to take the step, and this is where the human is taking the step. So we are using the angle difference between them to understand if actually we can solve this problem as an optimization problem. And when we look at the results, we are seeing that, yes, this angle difference is more or less close to what humans are doing, but not always. And then we are checking what's going on with the trajectories. We are also seeing that when we are not applying any assistance and still comparing what humans are doing and what the optimization results supposed to show, is that there is a difference. And when we look at the assistance, the difference is becoming smaller. Therefore, we can say that this controller is providing intuitive and natural user interaction. Okay. However, here's the glimpse of what it doesn't do. Here, for example, in this scenario, it didn't work very well. And the main reason behind this is that we cannot always understand which direction human would like to go. That's cool that we are saying that if you get the push from here, you can take the step like this, but it's human and it's not always taking the step to this direction. So this method is working up to some point, but definitely needs improvements. However, overall, this is the first time that we are showing we can provide a push recovery framework that is working in an omnidirectional manner. And we can run this one as an online method to understand the step position and the duration. And we can generate different strides to be able to keep our balance. Okay, so then we have handled what's going on when we are standing, but most of our daily living locomotion is not just standing. We are not just standing throughout the whole day, although it's some part of our daily locomotion. It's not always. We are usually walking, we are stair climbing, we are going down the stairs, we are walking on uneven terrain. So actually the controller should supposed to work and assist our users on those scenarios as well. Our goal in this work is to provide partial assistance to both gait and the balance. Up to today, many of the exoskeletons are providing assistance only to the gait, which means that if you are trying to do this movement, exoskeleton is just providing you additional torques to do this, but it doesn't consider how much that it is affecting your balance. And we would like to provide some guidance without constraining the movement, which means that users should still have some freedom to do their own movements. And we would like to integrate the natural foot placement and movement autonomy. So basically, exoskeleton is not in the charge, but exoskeleton and the user are cooperating between each other. To do so, I am taking advantage of the interjoint coordination. And interjoint coordination means that basically when I try to reach to this bottle, I'm not doing joint by joint movements. I'm not doing this and that, but I'm moving my arm in some kind of a synchronization in a harmonic way to be able to grab it. And this is what's happening when we are walking as well. We are walking, we are not doing this and that, and this is actually what's the result of it throughout one gait cycle, which means that from one heel strike to another one, the full cycle, this is what your hip flexion extension and knee flexion extension joints are doing. This is the heel strike, you go like this, you come back to this point. Up to this point, you are in the stance phase, and then you are swinging your leg. And when we look at the people with multiple sclerosis, this coordination is broken. For example, this is the healthy pattern. This is a pattern of a people with MS, which is less obvious, and the red one is the patient's weakest side that is showing the worst condition, what's happening to this coordination. And This interjoint coordination is cool, but since this is only focused on the sagittal plane, it doesn't provide any balance assistance. To be able to provide some balance assistance, we again need to focus on this degree of freedom, which is hip abduction adduction. To do so, I take a look at different data sets and analyze if this coordination pattern is also visible in 3D. And I have seen that, as you can also see from these figures, yes, it is. And therefore, we have developed this control strategy that I am calling 3D pet controller to provide assistance to the users to enable partial gait and the balance assistance. And this is what's going on. Let's say that this is the moment of where are you in your interjoint coordination pattern, which is including the hip flexion extension, knee flexion extension, and hip abduction adduction. And this is the healthy gait pattern, what humans are having when they are walking by considering these 3 degrees of freedom. And if you are here, this controller is providing assistance for you to go in this direction, come closer to healthy human pattern. And basically, you can assume this one that there are small springs around those to be able to gently push, come closer to this path. And it's exactly the same when you're inside. So if you remember this pattern, basically what's going on here is that if you're at this moment, we are finding the closest point to what healthy humans are doing and providing you assistance to go there. And overall, this is the vector space of how the assistance is working around this desired trajectory in 2D. I find this figure super intuitive. This is the control strategy, but do we know if it is working or not? To understand this, I'm asking 2 questions. The first one is that if this controller is allowing us to modulate the foot placement by changing the controller gains, can I enable different foot placements to be able to assist the gait and the balance? And if this controller allowing forgiveness, especially in the lateral direction, because we know that already it provides some forgiveness in the sagittal plane. So to understand this, I have done the experiments with narrow, normal, and wide steps while providing the same assistance conditions. And let's see with the first one. So what we would like to do is modulate foot placement. And to be able to do so, I get 6 subjects, ask them to walk on treadmill for 3 minutes under 4 conditions. And these 4 conditions are starting from no assistance when the exoskeleton is running in the zero torque mode, which is a mode that is allowing you to move exoskeleton as transparent as possible, which means that you are not feeling the inertia, damping, or any internal friction of the exoskeleton. Is it really the case? No, not really, because you cannot make any exoskeleton that is not grounded as super transparent as possible, but you definitely feel the difference, and it's a zero torque mode that I am calling. Basically, the exoskeleton is not resisting you to move. And there are 3 assistance conditions. When there is no assistance to hip abduction adduction, while keeping the assistance for the hip flexion extension to the same. And then I am increasing assistance to hip abduction adduction and maximizing assistance to hip abduction adduction. So the goal is to understand, by changing the controller gains to the hip abduction adduction, can we modulate the foot placement? And the result shows that from zero torque to no assistance, low assistance, and high assistance, we can actually modulate where people are putting their steps on the treadmill, which means that we can actually provide partial assistance to the gait and the balance. And also what we are seeing that when we are increasing the controller gains, we could able to come closer to our reference healthy pattern. And this is the part that we are showing that the gait assistance is working as well. So next part, as I have said, the exoskeleton controller should be cooperative with the user. It shouldn't be overriding what the user wants to do. Basically, exoskeleton is telling you to walk like this, but I don't want to walk like that. I would like to do this. So am I allowed to do this? Let's see. To be able to do so, I get 7 subjects. I ask them to walk on this treadmill with the patterns of the normal step width in 6 conditions. And these 6 conditions has no assistance conditions for narrow, normal, and wide steps, and the assistance cases, narrow, normal, wide steps. So basically, I would like to understand the difference between them. And when we look at the results here, what we are seeing is that dotted ones are when there is no assistance. This one, this one, this one, no assistance, no assistance, no assistance, no assistance. And the rest is the assistance conditions. For the anterior-posterior direction, we see that exoskeleton is pretty much allowing users to do as they were doing in no assistance condition, which is good because we are not overriding what human is already doing. And when we look at the medial-lateral direction, we are seeing that while we are increasing while we have the assistance, the conditions from the no assistance is actually different. The exoskeleton is allowing you to increase your step size while still allowing you to take some deviations. Again, as we have seen in the first experiment, from no assistance to with assistance, we are seeing a better alignment with the reference pattern that we would like to follow. As you can compare this and that, or this and that, you can definitely see that with the assistance, you can come closer to our healthy interjoint coordination patterns. So these were the 2 questions to understand if this developed controller is providing partial assistance. Can this controller modulate the foot placement through the hip abduction adduction assistance? That it is yes. And when we look at the controller, if it is allowing forgiveness in the lateral direction, the answer is yes. So in this study, overall, what I have done is that I have developed this 3D pet controller to provide assistance to the gait and the balance. And then I have developed and then this developed controller is effectively guiding the joint trajectories, that this controller allowing us to modulate this step width, and also that it is allowing to step deviations. So I have talked about walking on the treadmill, walking over ground up to this point, but I was saying that this assistance should be providing for different daily living activities, such as stair ascending, stair descending, and ramps, which are currently unpublished. So here, just a video that hoping that you can also see the difference between passive exoskeleton that you are seeing, that I am going through the stairs, and when we are running with the controller. I don't know if it is clear for you, but I'm just gonna run one more time because for me it's super obvious to see the difference between the passive version and the assistance conditions. And hopefully I'm gonna talk about them later on at some point in the future. So finally, we have the walking over ground. We could actually, even though I didn't talk much about the staircases, we can actually do the stairs, but how we can understand the transitions between them. Transitions are super important because currently what's happening is that you are walking over ground and this is your daily life. You are going down, but the exoskeleton cannot actually support this because there is either user selection mode that is choosing you to take a step downstairs, or there is operator, FA is just pressing some buttons so that I can take step downstairs. So basically, your exoskeleton should be providing your movement autonomy throughout different daily living activities. And to do so, we need to understand the transition between activities. In this study, I have used 2 exoskeletons. Up to now, you got familiar with the Autonomio, and the second exoskeleton is called Evoke. Evoke has one active degree of freedom for the hip flexion extension, which is this. And it is much more easier to use and quite lightweight to wear. We also have access to ground reaction, We don't actually have ground reaction forces, but we have ground contact information with evoke. And this is autonomio that you already know. And by using these two exoskeletons, we are trying to understand the transitions. And this is how people have done already. This is the group of Robert Gregg. They have developed this state machine by using by training 3 different classifiers between walk to sit, walk to stair ascent, and walk to stair descent, and vice versa, through instantaneous characteristic features. These features are kinematics based, such as hip angle at the maximum hip flexion extension, hip angle when you have the contact with the ground, and the difference between the minimum hip angle. So these are the features that has been developed to be able to train those classifiers. And we have adapted the same state machine, and we did simply change those classifiers to use in the thresholds, because unfortunately our computing capabilities on the exoskeletons are still limited. Even nowadays are getting better and better. We are still limited in the computational resources. And then once we repeated everything, so here's an example of the characteristic features. This is the hip angle at the maximum hip flexion. And this figure is important because I'm going to tell something in a couple of slides later on. We have utilized exactly the same state machine. Then we have checked the results, comparing the training and the test accuracies from the different data sets that is available. We have seen that, okay, they are doing well. Then we wanted to test everything with the exoskeletons. We have asked 18 subjects to stand up here, then walk, climb stairs, transition to walk again, go there, sit, and come all the way back. And each subject has repeated this not that small path 5 times. And we have evaluated the accuracies by considering if we could able to detect 5 out of 5 transitions as 100%, and if we could able to detect only one as 20%. So basically, we have only one moment to understand if this is a correct transition or not. And this is how it looks like in the experiments. So as you can see, the subject is climbing the stairs. We are putting the ground truth information while following them. And they are sitting over there, and they will go down, come back all the way down. And you can see how the real-time transition detection accuracies are going. Let's see if we could able to detect this. Yay, we have detected that they are going downstairs. So now we can actually change the controller to assist the user in those conditions. And we have actually done these experiments first time with the evoke exoskeleton. So I'm asking you to only follow the green ones. As you can see, the median accuracies are quite high with the evoke. And then we have repeated the same experiment with the autonomio. And as you have seen, evoke and autonomio has quite different in terms of their kinematics and in terms of their weight. And therefore, the results of autonomio, actually we didn't know at that moment if it is because of this, but we have seen that there is a difference. It was working well with the evoke. It wasn't working that well with autonomio. And then we have investigated all the experiment videos, what's going on. So what we have seen is that when people are sitting with autonomio, they were not just sitting like this, but they were like doing tiny steps so that they can adjust the weight of the autonomio. Or they were taking very slow sitting dynamics, as we are seeing over there. It's slow. Or some people has different preferences. As you can see, they are like running through the stairs. This is not in our training data set. Or someone is going very, very slow. Someone scared, super slow. These are completely different data sets for us to be able to use those same thresholds for everyone. Therefore, we have come up with 2 personalization strategies. One of them is based on the kinematics, statistics-based kinematics understanding, and we have developed a method to adjust the threshold. Requiring some post-processing, we wanted to implement a different strategy, which is Bayesian optimization, as it is super applicable for this scenario. And after the Bayesian optimization, we have able to tune all of those thresholds for different systems and different people. And when we look at the accuracy results, we have seen that the accuracies are improved compared to without personalization. Here, for example, we can see that it has increased by 20%. Here, we have seen that it has increased 80%, 60%, and there are also some cases that we didn't see any improvement, which means that the problem with those conditions was not in the thresholds, but in the conditions of going to those states, which are not optimized at this moment. So overall, in this study, what we have done is we have developed a transition detection strategy to be able to ensure reliability and adaptability between conditions. And we have developed 2 personalization strategies to be able to tune our system to individual gait patterns and different system characteristics. And as a result, we also published an open source data set of lower limb kinematics from 18 subjects using 2 different exoskeletons, which I find quite exciting as well, because there are a lot of kinematic data sets of the humans are walking by themselves, but there is not much of data when people are walking with the exoskeletons. And I think it's a clear resource to be able to use later on. And overall, this is what I have talked today. I have talked about partial assistance during standing, partial assistance during daily living activities, and how we can detect the transitions between them. And in this partial assistance during standing, we have developed this push recovery framework that is working in an omnidirectional manner for the first time in the literature, and that it is quite compatible with what human wants to do. And in the partial assistance during daily living activities, I had developed the 3D pet controllers that is modulating the step width, that is allowing us to keep our gait and the balance assisted. And we have improved actually I haven't showed the results here, but there is a clear difference in the user comfort and the perception of how the exoskeleton is helping when you change the controller parameters. And finally, we have developed a system to be able to detect the transitions between different activities. And overall, that's the end of my PhD, and I would like to thank you all throughout my whole studies from ODTÜ, from Sabancı, and at EPFL. So I'm really grateful for all of my friends, my colleagues, my supervisors, and thanks a lot.